Yogesh Prajapati, am I audible? Mr. Yogesh Prajapati, can you hear me? Hello? Hello? Mr. Yogesh Kumar Prajapati, you are supposed to join to the other link. Hello? Hello. Hello.
Hello.
Hello.
Hi, can you hear me?
Am I audible? Mr. Yogesh Kumar Prajapati, if you can hear us, you are supposed to join to TAS Raghavan link. Welcome back to session 13. This is a contributory session, and in this session we have with us Ms. Sonali Sharma from Malaviya National Institute of Technology, Jaipur, India. She'll be talking on structure of the W solution set of the tensor complementarity problem. Another speaker is Vaibhav Shekhar from National Institute of Technology, Raipur, India. Title of his talk is more on convergence of two-stage alternating iterative scheme. And the third speaker is Mr. Puneet Kumar Yadav from Malaviya National Institute of Technology, Jaipur, India. He'll be talking on the range, column sufficiency, and the pseudo SSM property of linear transformations on Euclidean Jordan algebra. Another speaker is Miss Milicia Anzel from Kuwait University, Kuwait. She'll be talking on chain graph sequences and Laplacian spectra of chain graphs. And the last speaker is Mr. Krishna Kumar G from University of Kerala, Thiruvananthapuram, Kerala. Title of his talk is Condition Eigenvectors of Bounded Linear Operators. May I now request Professor M. Rajesh Kannan from Indian Institute of Technology, Kharagpur, India, to chair this session. Professor,
Yeah, thank you.
please.
Can you hear me?
Sir, can you? It's little bit low. Your voice is little bit low.
Okay. Can you hear me now? Okay. Good morning, everybody. Our first speaker is Ms. Sonali Sharma. Sonali, are you here?
Yes, sir.
Yes, yes. Yeah. So we will play the video. Before that, if you want to say something, you can say.
No, sir. Actually, yes, my video can play.
Okay.
I am Sonali Sharma, a research scholar from Department of Mathematics, MNIT Jaipur. Today, I am here to present the talk on the topic structure of the W solution set of the tensor complementarity problem. Here is the outline of my presentation. So let me start with the introduction. Tensor. Tensors are multi-dimensional analog of matrices, and they are also referred as hypermatrices. For any two given natural numbers m and n, an mth order n-dimensional real tensor is of the form A is equals to A I1 I2 In. Here the indices I1, I2, In varies from 1 to n, and here we can see that if m is equals to 2, then a tensor is just a matrix. Tm, n denotes the set of all mth order n-dimensional real tensor. For any tensor A, its each entry with I1 is equals to I2 is equals to Im is called a diagonal entry of A, and the rest are off diagonal entries. A tensor is said to be symmetric if it is invariant under any permutation of its indices, and Sm, n denotes the set of all mth order n-dimensional real symmetric tensor. For an mth order n-dimensional real tensor A, we define a function f from Rn to Rn whose ith component is given by this equation 1. Here note that each component of f is a homogeneous polynomial of degree m-1. We write f of x is equals to ax to the power m-1, and for any vector x in Rn, we define the inner product of x with f of x equals to ax to the power m. The linear complementarity problem. So let A be a given real matrix of order n and Q be a given vector in Rn. Then the linear complementarity problem is to find a vector x in Rn such that x is non-negative, W is equals to Ax plus Q is non-negative, and x transpose W is equals to 0. Here x non-negative means each component of x is non-negative. This problem is denoted by LCP A, Q, a pair of vectors x, W such that they satisfy this equation 2, 3 and 4 is called a solution of the LCP A, Q. The vector x is said to be a x solution if there exists a vector W such that these three equations are satisfied, and the collection of all such x is denoted as SOL A, Q and said to be the solution set of the LCP A, Q. Similarly, the vector W is said to be a W solution of the LCP if there exists a vector x such that these three equations are satisfied, and the collection of all such W is denoted by W SOL A, Q, and it is said to be the W solution set of the LCP A, Q. Now, column competent matrix. A matrix A is said to be column competent if x star Ax equals to 0 implies Ax equals to 0. Here star is the Hadamard product of x and Ax. Column adequate matrix. A matrix is said to be column adequate if x star Ax less than equals to 0 implies Ax equals to 0. The motivation behind reading these type of matrices is due to the uniqueness of and finiteness of the W solution to the LCP for column adequate and column competent matrix. It was proved by Ingleton that a matrix is column adequate if and only if the W solution to the LCP is unique for all Q in Rn. In 1999, Somschuk proved that a matrix is column competent if and only if the LCP has finitely many W solution for all Q in Rn. Another well-known result in matrix theory is that if A is symmetric matrix, then A is column adequate matrix if only A is positive. These results can be extended to the tensor complementarity problem. Here we have tried to extend these results to tensor complementarity problem. The objective of this talk is to talk about the extension of column adequate and column competent matrices to tensor and analyze about the corresponding W solution set to the tensor complementarity problem. First of all, let us define the tensor complementarity problem. So let f of x is equals to ax to the power m minus 1 and q be a given vector in Rn. The tensor complementarity problem is to find the vector x in Rn such that x is non-negative, w is equals to f of x plus q is non-negative, and x transpose w is equals to 0, or to show that no such vector exists. Now this problem is denoted by TCP A, Q. The collection of all such x is said to be the solution set of the TCP A, Q, and it is denoted by SOL A, Q. Similarly, the collection of all such W is said to be the W solution set of the TCP A, Q, and it is denoted by WSOL A, Q. Now let me define some well-known tensors in the literature. First is positive semi-definite tensor. A tensor is said to be positive semi-definite if for any vector x in Rn, ax to the power m is always non-negative. P-naught tensor. A tensor is said to be P-naught if for any non-zero vector x in Rn, there exists an index I such that xi is non-zero and the product of the ith component of x and ax to the power m minus 1 is non-negative. Next is co-positive tensor. A tensor is said to be co-positive if for any vector x in Rn plus ax to the power m is non-negative. Here Rn plus is the collection of all those vectors in Rn whose each component is non-negative. Next is Z tensor. So a tensor is said to be Z tensor if all of its off-diagonal entries are non-positive. Column sufficient tensor. A tensor is said to be column sufficient if any vector x in Rn satisfies the condition that whenever x star ax to the power m minus 1 is less than equals to 0 implies x star ax to the power m minus 1 equals to 0. Now, if a vector x in Rn plus satisfies this condition, then we say that it is column sufficient tensor on Rn plus. R0 tensor. A tensor is said to be R0 if TCP A, 0 has 0 as the only unique solution of this TCP. Now we have extended the column adequate matrix and column competent matrix to tensor case, and here is the definition. First is column competent tensor. A tensor is said to be column competent if a vector x in Rn satisfies the condition that whenever x star ax to the power m minus 1 equal to 0 implies ax to the power m minus 1 equals to 0. Now the vector x belongs to Rn plus, then we say that it is a column competent tensor on Rn plus. Column adequate tensor. A tensor is said to be column adequate if x in Rn satisfies the condition that whenever x star ax to the power m minus 1 less than equals to 0 implies ax to the power m minus 1 equals to 0. Here, if the vector x belongs to Rn plus, then we say that it is column adequate tensor on Rn plus. Now, for these type of tensors, we have obtained some equivalence results. First is for the class of symmetric tensors. So theorem 1 states that let A be a symmetric tensor of order m and dimension n, then the following conditions are equivalent. A is positive semi-definite, A is column adequate, A is column sufficient, A is P0. So here we can see that the well-known result in matrix theory for symmetric matrices can be extended to the tensor case also. Next result is for the Z tensor. Let A be an even order Z tensor, then the following conditions are equivalent. A is column adequate, A is column adequate on Rn plus, A is column sufficient on Rn plus, and column competent. Next is we have observed about the W solution set of the tensor complementarity problem corresponding to column competent tensor, and we have obtained the result that the column competent tensor need not have finitely many W solution. The given example is the counter example for that. Also, if a tensor has finitely many W solutions, then it need not to be a column competent tensor. Below is the counter example. Now we investigated the result for the two-dimensional case and we have given a positive answer. Theorem 3. Let A be an mth order two-dimensional tensor, then the following are equivalent. A is column competent. For all Q in R2, the number of W solution of the TCP A, Q is finite. Next result is for the well-known class of co-positive tensor. Let A be a co-positive tensor, then A is column competent on Rn plus if and only the W solution set of the TCP is singleton for all Q in Rn plus. Next results are for column adequate tensors. The column adequate tensor need not have singleton W solution set. Here is the counter example for this. Now we have given a class of tensor for which the equivalence holds. So let A is a column adequate tensor on Rn plus if and only if W solution set is a singleton set for all Q in Rn plus. In order to understand more about the uniqueness and finiteness of the W solution set, we have defined column competent property, which is the definition is given as follows. A tensor A in Tmn is said to have the column competent property if x and y in Rn satisfies x minus y star fx minus fy equals to 0 implies fx equals to fy. Here we can see that for m equals to 2, the definition of column competent matrix, column competent tensor, and column competent property coincides. Now for a tensor having a column competent property, we have obtained the following result. Theorem 6. Let A belongs to Tm, and be a R0 tensor. If A has a column competent property, then the W solution set of TCP is a finite set for all Q in Rn, and the converse of theorem 6 need not to hold. This is the counter example for that. Now, all of these results we have obtained has been summarized in the article Structure of the W solution set of the tensor complementarity problem. Here are the references. Thank you.
Okay, yeah. Thank you, Sonali, for the interesting talk. Audience, if you have any question, we can ask. Okay, I have a quick question. In one of your theorem, I think theorem 1 or 2, you have given a necessary and sufficient condition for a positive semi-definiteness of tensors, right? In terms of column sufficient and other.
Yes, sir.
So, yeah. So in that slide, I didn't see the assumption m is even. Do we need m is even there?
Yes, sir. It will not obviously imply because it is symmetric and positive semi-definite, so that will imply m is even because there does not exist an odd order symmetric positive semi-definite tensor.
Yes. That's right. But the theorem was giving equivalent condition in terms of other properties which you defined, like column sufficient and all.
Yeah.
The other conditions will holds for any tensors, irrespective of whether even order or odd order.
No,
You'll find
actually
non-trivial.
No, actually we have given some lemmas which prove that there does not exist odd order column adequate tensor, and using
Oh,
that we have given this equivalence.
Okay. So M is even there.
Yeah.
Okay. Are there other questions? Okay. If not, let us thank Ms. Sonali.
Yeah. Thank you, sir.
Yeah. The next speaker is, I think, Vaibhav. Mr. Vaibhav Shekhar.
Yes, sir, I am present.
You are here. Okay. Yeah. Please play the video. Do you want to say something before starting the video?
No, sir, just I want to thank the organizers to give me a chance for presenting a paper. That's all.
Okay. Yeah. Thank you. Yeah, please play the video.
For giving me an opportunity to present a paper in this conference. I am Vaibhav Shekhar, a research scholar in the Department of Mathematics, NIT Raipur. The title of my presentation is more on convergence of two-stage alternating iterative scheme. This is the outline of my presentation. We will start with introduction and preliminaries. Then we will talk about two-stage alternating iterative scheme. We will talk about the convergence of this iterative scheme in section 3 under the main results. And then we will see some conclusions. So we will start with a class of matrix called a Z matrix. When a square matrix over a real field R is called a Z matrix if its off diagonal entries are non-positive. Now this class of matrix contains a special class of matrices called an M matrix. So given a Z matrix A is called an M matrix if it can be expressed in the form of Si minus B, where S is a positive scalar, B is a non-negative matrix, and S is greater than or equals to the spectral radius of B. Here we have considered a matrix of size 2 cross 2, and we can see that if we choose S to be a 2, then we can express it in the form of Si minus B, where B is a non-negative matrix. And further, we can verify that the spectral radius of B is equals to 1, which is of course less than the scalar value S. So we can conclude that this matrix A is an M matrix. Now we will talk about the splitting. So given a system, linear system X is equal to B, if we decompose the coefficient matrix A in the form of U minus B, then this is called splitting whenever U is non-singular. With the help of this splitting, we are actually interested in solving a system of linear equation iteratively, where the coefficient matrix of this system A is very large and sparse. So if we put this expression in this equation number 1, we will get equation number 2, which is called the iterative scheme corresponding to this splitting. And here the matrix T is called the iteration matrix of this method. Varga proved that this iterative scheme, equation number 2, will converge if and only if the spectral radius of the iteration matrix T is less than 1. Now we will talk about a class of matrices which contains an important class of matrices. So the class of monotone matrices contains class of non-singular A matrices. So given a square matrix A over real field is called monotone if Ax non-negative implies X non-negative. And Lossel Collage provided one wonderful characterization of this class of matrices. He proved that A is monotone if and only if A inverse exists and its inverse is non-negative. In this table, we have different classification of different kinds of splittings. So we have given A is equal to U minus B is called a regular splitting. Whenever U inverse and B both are non-negative is called weak regular splitting of type 1. Whenever U inverse B are non-negative. And it is called weak regular splitting of type 2 whenever U inverse B, U inverse both are non-negative. And we can see that the necessary and sufficient condition for the convergence of the iterative scheme corresponding to these three class of matrix splitting is that the matrix A should be monotone. Now we will talk about two-stage iterative scheme. So we are given with a linear system Ax is equal to B and a splitting of A is equal to U minus B. With this splitting, we get equation number 3 as earlier. Now this equation can be written in the form of a linear system uy is equal to b tilde, where b tilde is b xk plus b. Now we will solve this equation number 4, that is this linear system, using another iterative scheme formed by this splitting u is equal to f minus g. So whenever this procedure is followed, this is called two-stage iterative scheme, and if we mathematically write this procedure in a single iterative scheme, we will get equation number 5. Now we have another iterative scheme called alternating iterative scheme. Here we have two splitting of the coefficient matrix A, and with the help of these two splitting, with the help of first splitting, the first half of the iterate is obtained, and next half of the iterate is obtained using the second splitting. And if we eliminate x k plus 1 by 2 from these two equations, we will get equation number 7, which is in the form of single iterative scheme. And here H is given by this expression x inverse y u inverse v is the iteration matrix of this iterative scheme. Benji and Sichel proved this result, which says that we have a coefficient matrix A which has two splitting u minus v and x minus y, and both are weak regular splitting of type 1. And suppose A is monotone, then in that case, the iterative scheme corresponding to this matrix splitting will always converge. That is, whenever A is monotone and we have splittings, any two splittings of weak regular splitting of type 1, then the iterative scheme will always converge. Further, they proved that the unique splitting f minus g induced by the iteration matrix H is also a weak regular splitting of type 1. Now the same work was being carried forward by Climate and Peria, and these results are being taken from their paper, which was obtained in 2003. The first result says that we have splittings of the matrix A, and both are type 2 weak regular, and the coefficient matrix A is monotone. Then in that case, the iterative scheme, the alternating iterative scheme will always converge. And further, they proved that the unique splitting induced by the iteration matrix H is also of the same type, that is weak regular splitting of type 2. And here one corollary which talks about the convergence rate of the alternating iterative scheme. So we have two splittings, both are weak regular splitting of type 1 and type 2. And with given condition that A is monotone, then in that case, the spectral radius of this matrix is always less than equals to the spectral radius of these two individual matrices. So recall that this was the iteration matrix of the iterative scheme corresponding to alternating iterative scheme. So it says that under this sufficient condition, the alternating iterative scheme always converges faster than the single iterative scheme. Now this theory has some drawbacks which we will discuss in this section. So suppose our coefficient matrix is in this form, and if we calculate its inverse, then we can see that it is not non-negative. So in this case, the existing theory, whatever we talked about in the earlier slides, will fail, and we want to avoid this kind of situation. So to avoid this kind of situation, the usual non-negativity is replaced by a more general cone non-negativity. So for that, we will take the help of a new notion called proper cones. So a non-empty subset K in Rn is called cone whenever lambda k is contained in K for all non-negative lambda. A cone is called a convex when it is closed under addition. A pointed cone whenever the intersection of K and minus K is singleton 0. Solid cone if interior is non-empty. A closed pointed solid convex cone is called a proper cone. Now we will see some example of proper cones. So the first example is non-negative arthant of R2, and it is a proper cone. The second one is a subset of R3 denoted by K3. It is also called an ice cream cone, and this is also a proper cone. R2 is not a proper cone because it is not pointed. We can observe this. Singleton 0 is not solid. That's why it is not a proper cone. And finally, this set is not closed, so it is also not a proper cone. Now, the general non-negativity, that is the usual non-negativity, is also generalized in case of cone non-negativity. So given any vector x in Rm is called k non-negative whenever this vector belongs to that set k, and we denote it in the form x greater than or equals to subscript k 0. That is, x is non-negative with respect to this proper cone k. And the same things have been extended in case of a matrix. So real n cross n matrix A is called k non-negative whenever k is invariant under k. That is, ak is contained in k, and we denote this as a greater than or equals to subscript k 0. That is, a is non-negative with respect to the proper cone k. Here one example we can see that we have considered k3, that is the ice cream cone. With respect to this proper cone, the same matrix which we had discussed, that this is not non-negative with respect to usual non-negativity, but here with respect to this proper cone K3, this matrix A inverse is in fact a non-negative matrix. Now we will discuss about two-stage alternating iterative scheme. So as the name suggests, two-stage alternating iterative scheme. So we are somehow merging two basic iterative schemes, two-stage and alternating iterative schemes. So we will get equation number 8 of this form by using the splitting is equal to b minus c, and with the help of this splitting, we can write the system by is equal to b tilde, where b tilde is given by this expression. Now we want to solve this system again, but this time we will not use single iterative scheme, rather we will apply alternating iterative scheme. So we will require two different splittings of the coefficient matrix B. And if we eliminate here xk plus half from these two equations, we will get equation number 11. And if the whole procedure is represented in a single equation way, then it will look like equation number 12 that is given in the last line. And the same iterative scheme can be written in a more simpler way, where the iteration matrix, its expression given by equation number 14, has been considered as TSK, and CSK is as this matrix. And this two-stage alternating iterative method is called stationary whenever xk is constant for all k. McCallum et al. Proved this result for the convergence of this kind of iterative method. So he proved that whenever this splitting is equal to b minus c is a convergent regular splitting, and these two splittings of b are convergent weak regular splitting of type 1, then in that case the stationary two-stage alternating iterative scheme given by question number 12 that we saw in the earlier slide always converges for any sequence xk. And now, based on this literature, we have obtained some results. So the first result is, so basically I have obtained these results on more general setting, that is in proper cone setting. So it expands the scope of this result. So the first result says that we have a k regular splitting of a matrix A, of a k monotone matrix A, and we have two k weak regular splittings of type 1 of the matrix P. Then in that case, the stationary two-stage alternating iterative scheme will always converge for any in a sequence of vectors. The second result says that the same sufficient condition is not enough to guarantee the convergence in case we have k weak regular splitting of type 2. In this case, for type 2, we required these two additional conditions. So C U inverse V is equals to V U inverse C. Similarly, C X inverse Y should be equals to Y X inverse C. And then we can guarantee that the convergence is always guaranteed. And here one example to demonstrate this theorem. So we have given a subset of R3, that is K3, which is an ice cream cone, and this one splitting of the coefficient matrix A, which is convergent K3 weak regular splitting, in fact. And this matrix B has two splitting, and both are K3 weak regular splitting of type 2. And in this case, we have chosen U and X to be as this matrix, with Xk is fixed as 2. Now we can see that if we compute C U inverse V and V U inverse C, then both are equal. Similarly, Cx inverse Y and Yx inverse C is also equal. So the sufficient condition is satisfied. So from here we can say that the corresponding iterative scheme will always converge in this result. And in fact, we can verify that the spectral radius of the iteration matrix TSK is equals to 0.5367, which is less than 1. So the theorem is validated through this example. Now we have obtained 2 more results. The first result is for type 1 case, while the second result is for type 2 case. So this splitting is k-weak regular splitting of type 1, and this result says that under this sufficient condition given by equation 15, the iterative scheme will always converge monotonically. That is, here we can see that the xk is a decreasing sequence, while xk is an increasing sequence, and both converges to the unique solution A inverse B of the linear system Ax is equal to B. While the second result is for type 2 case. So here we have these two splitting are of k-weak regular splitting of type 2. And here also we are required to add these two extra conditions that was not present in the last result. And here also, if we add these two results, then this theorem guarantees that under this sufficient condition given by equation number 16, the iterative scheme will converge monotonically. And now we have considered one example. We have considered a Laplace partial differential equation with a Dirichlet boundary value problem, and with equal grid spacing, H is equal to delta X equal to delta Y. And we know that if we discretize this using central different discretization, we will get a system of linear equation of the type Ax is equal to B, and we require to solve this linear system to obtain the approximate solution. So we have applied our two methods, two-stage and simple two-stage method and two-stage alternating iterative scheme to get the solution. And we can see that we have compared these two method, and this represents the spectral radius of the corresponding iterative scheme. You can see that the spectral radius corresponding to two-stage alternating iterative scheme is less as compared to the simple two-stage iterative scheme. And so it is not surprised that the iteration of the iterative scheme corresponding to two-stage alternating iterative scheme is quite less as compared to the simple two-stage iterative scheme, and the same can be observed from as the size increases of the matrix. And this one example is also a comparison table which shows that the convergence of two-stage alternating iterative scheme need not be, it does not guarantee that the two-stage also converges. So here we have a different size of coefficient matrix, and we can see that the spectral radius corresponding to two-stage iterative scheme is greater than 1. So of course, the iterative scheme will not converge, while in case of two-stage alternating iterative scheme, it is converging, while the simple two-stage method is not converging. So finally, the conclusion part. So we have established the convergence of two-stage alternating iterative scheme when the second splitting is k-weak regular of type 1 and type 2 both. And we have also shown the computational advantage of the discussed two-stage alternating iterative scheme. It is faster than the simple two-stage iterative scheme. And these are my references. Thank you.
Yeah, thank you, Vaibhav, for the interesting talk. Yeah, audience, if you have any question, can ask now. Okay, if there is no other question, let us thank Vaibhav again. Yeah, Vaibhav, thank you so much.
Thank you, sir.
Yeah. Yeah, our next speaker is Punit Kumar Yadav from Malavia National Institute of Technology. Is Punit?
Yes, sir, I am here.
Okay, okay. Yeah. Please play the video.
Yes, sir, you can play the video.
Yeah.
Okay. Hello, everyone. My name is Punit Kumar Yadav. I am a PhD research scholar of Department of Mathematics, Malavia National Institute of Technology, Jaipur. The title of my talk is The Range Column Sufficiency and the Pseudo-Essm Property of Linear Transformations on Euclidean Jordan Algebra. It is a joint work with Dr. K. Palpandi, who is also my PhD supervisor. His outline. Introduction. Given n cross n real matrix A and n vector Q belongs to Rn, then the standard linear complementarity problem is to find a vector x in Rn such that x belongs to Rn plus, Ax plus Q belongs to Rn plus, and x transpose Ax plus Q equal to 0. There are various classes of matrices which give us the solution structure of LCP. We will look at here column sufficient matrices. A matrix A is said to be column sufficient if x star Ax equal to 0, whenever x star Ax less than equal to 0 and x belongs to Rn. Here star is Hadamard product. We have following factorization for column sufficient matrices. Now we will look at here and another class of column sufficient matrices, which is range column sufficient. A matrix is range column sufficient if x in range of A, x star Ax less than equal to 0 implies x star Ax equal to 0. We have following theorem for range column sufficient matrices, which states that A be a range column sufficient matrix, then intersection of solution set of A LCP with a range of A is a convex set for all Q belongs to Rn. A question can be proposed here whether range column sufficient matrix can be generalized for linear transformation on Euclidean Jordan algebra. And now we look at another class which is strictly range semi-monotone. A matrix is strictly range semi-monotone if x greater than equal to 0 belongs to range of A, x star Ax less than equal to 0 implies x equal to 0. And we have following equivalence relation for range semi-monotone matrix. The range semi-monotone matrix is generalized as the pseudo-Essm property on symmetric space and Hermitian space. So another question can be proposed here whether the PSSM property can be generalized to the Euclidean Jordan algebra, and is there any relation between PSSM and range column sufficiency? We will give some answer here. Notations: Rn, Rn plus, Rn cross n, Sn, Hn, Sn plus, Hn plus. Euclidean Jordan algebra. A triple is a Euclidean Jordan algebra if V is finite dimensional inner product space over R and the bilinear map satisfies following conditions for all x, y, z in V. The symmetric cone K is a set of square in V, and K is, we can see here, a self-dual closed convex cone. Also, we say x belongs to K if and only if x is greater than equal to 0. Example: V equal to Rn is a standard example for Euclidean Jordan algebra. Here inner product is user inner product and Jordan product is Hadamard product. And for V equal to Sn, the symmetric space, for trace inner product, and for Jordan product 1/2 xy plus yx, Sn is Euclidean Jordan algebra where k equal to Sn plus. Jordan frame. A set of primitive idempotent in V is called Jordan frame if it satisfies this condition, where E is identity element in V. We can see that idempotent element V is an element who is equal to its self square, like that we can say x is an element which is idempotent if x square equal to x, and if it is non-zero and it is a not sum of two non-zero idempotent element, then we will say it is a primitive idempotent. Spectral decomposition. For any x in V, the spectral decomposition of x says there exists a Jordan frame and real numbers lambda I such that x equal to sum of lambda is ei for I equal to 1 to r, where lambda is the eigenvalue of x, operator commute. Fix A belongs to V, then a linear transformation LA of x equal to A Jordan product x, then two element x and y are called operator commute if Lx Ly equal to Ly Lx. We have following lemma, which is very important in Euclidean Jordan algebra. For any two element x and y in V, we say x and y operator commute if and only if x and y have their spectral decomposition with respect to a common Jordan frame. Linear complementary problem. Given a linear transformation L on Euclidean Jordan algebra V and Q belongs to V, then LCP is to find a vector x in K, y equal to Lx plus Q in K, and their inner product equal to 0. For V equal to Rn and K equal to Rn plus, we will get standard LCP, and V equal to Sn, K equal to Sn plus, we will get semi-definite LCP, in short SDLC. Here are some properties of LCP. Given a linear transformation L on V, we say L has the Monotone property, range cross commutative property, pseudo Essm property, column sufficient property, and range monotone property. Jet transformation. A linear transformation L is called jet transformation if x and y in K, inner product of x and y equal to 0 implies Lx comma y is less than equal to 0. Here are some examples. For matrix with off diagonal entries are non-positive is Z matrix. For V equal to Sn, we have Lyapunov transformation and Stein transformation. Both are Z transformation. Group inverse. Group inverse is one of a kind generalized inverse. Also, it is a Drazen inverse. And we define here as the group inverse of a matrix A is a unique matrix X which satisfy following conditions. And for group inverse of a linear transformation, we say the group inverse of a linear transformation is a linear transformation L on V satisfies T L T equal to T, L T L equal to L, L T equal to TL. Now we look at here some existing result for range column sufficiency. That A is a real matrix. If A is a range column sufficient, then following statements are hold. And second result is that A be a Z matrix which is also range monotone. Then the following statements are equivalent. X is greater than equal to 0 and X is in range of A. X star X less than equal to 0 implies X star Ax equal to 0 and A is strictly range semi-monotone. And now we will define range column sufficiency on Euclidean Jordan algebra. Let L be a linear transformation on V. Then we say L has the range column sufficiency property, in short RCS property, if X in range of L, X and Lx operator commute, X Jordan product Lx less than equal to 0 implies X Jordan product Lx equal to 0. If we take here X in cone K, then we will say it is a range cone column sufficiency property, in short RCCS property. Now we will give some results. First result about automorphism invariance. Let L be a linear transformation on V and L cap defined as follows. If gamma is orthogonal automorphism, then L has the RCS property if and only if L cap has the RCS property. In this result, we characterize intersection of solution set of LCP with a range of L by the RCS property and range cross commutative property. PSSM property. Let L be a linear transformation on V, then L has the PSSM property if it satisfies x greater than or equal to 0 as well as x belongs to range of L, x and Lx operator commute, x Jordan product Lx less than or equal to 0 implies x equal to 0. We have following result for PSSM property. Let L be linear on V, then the following are equivalent. L has the PSSM property and the range cross commutative property on K. Second, solution of L comma Q intersection range of L equal to 0 for all Q belongs to K. Now in this section we will look at here the equivalence of RCS and PSSM property for some special transformation. First is Lyapunov transformation. If A is complex matrix and group inverse of Lyapunov transformation exists, then following are equivalent. A is semi-positive stable. Lyapunov transformation has PSSM property and Lyapunov transformation has RCS property. And we have proved similar result for Stern transformation, which is as follows. Now we will discuss here a class of first operators. Let B, C1 and so on Ck belongs to complex matrices. Then we define a linear transformation T on Hn by Tx equal to Bx B star minus I equal to 1 to K sigma Cix Ci star. Here B star is conjugate transpose of B. For B equal to A plus identity, K equal to 2, C1 equal to A and C2 equal to identity. The operator T reduces to the Lyapunov transformation. And if we take B equal to identity, K equal to 1, C1 equal to A, then we get the Stern transformation. And from the previous theorems, we can see the PSSM and RCS property both are equivalent for Lyapunov and Stern transformation. So motivated by this, we prove the equivalence of PSSM and RCS property for a new special case, that is let Lx equal to Ax plus x A star minus Ax A star, and if Ls exists, then following are equivalent. That is, L has the PSSM property and L has the RCS property. Now we will discuss equivalence of PSSM and RCS property for range monotone jet transformation. Let L be a range monotone jet transformation on V, then following are equivalent. L has the RCS property, L has the PSSM property. And in the end, we prove that let L be a self-adjoint jet transformation, then monotone, the column sufficiency, the range column sufficiency, the range cone column sufficiency, and the PSSM property all are equivalent. And here are references. Second and third reference, that complementary properties of singular M matrices, and second one is extension of P property, R property. These are main references for my talk, and thank you.
Yeah, thank you, Puneet, for the interesting talk. Yeah, audience, if you have any question, can ask. Okay, if there is no other question, let us thank Puneet. Yeah, thank you, Puneet.
Okay, sir. Thanks.
Our next speaker is Professor Melisha Angelique. Yeah, Professor?
Yes.
Yeah.
Here.
Yes.
Can I share this? Because I didn't send the video. Can I
okay, yeah, sure.
Yes. So let me share the screen with you. Can you see?
Yes, it is visible now. Yeah.
Okay. Just let me make. Sorry. Okay. So can you? Sorry.
Full screen? Do you want to make full screen?
Yes, but I don't know currently how can I do this.
Okay. Control L. Press this. Yeah.
Control
L. Yeah. That may help.
Is it now? I don't know. Something is not working properly.
Okay.
I don't know how to. No, so I did something wrong. Sorry. Sorry, I will do again. Sorry, I made something wrong here. Sorry. Okay, is it now full screen?
Yes, it is full screen.
Okay,
Perfect.
I'm sorry for the delay. Okay, so I'm going to talk about chain graph sequences in Laplacian spectra of chain graphs, which is my joint work with my colleague Abdullah Lazmi from Kuwait University, King Kardas from Korea, and Carlos Fonseca, also working in Kuwait. So the first motivation, why do we consider chain graph sequences and chain graphs, is coming from threshold graphs, because chain graphs serves as analog of threshold graphs. So in the class of connected graphs, it is known, if you consider graphs of fixed order and size, then the ones with the maximal index with respect to the JCC matrix and also with respect to sinus Laplacian matrix are threshold graphs. And then if we reduce ourselves to bipartite case, so we consider bipartite graphs of fixed order and size, then the corresponding maximizers with respect to both spectra are chain graphs. So, and there are important results on relation of degree sequences of threshold graphs and their Laplacian spectra. So if you know the degree sequence of threshold graphs, then you can deduce also what is a Laplacian spectra. So this motivated us to consider the relation with respect to degree sequences and Laplacian spectra of chain graphs. Another thing that motivated us to consider this is applications of possible applications in control theory. In this sense, as we can see later, we can construct some new classes of so-called controllable graphs. Okay. So just a brief introduction. So we consider graph G, which is an ordered pair of vertices and edges. We consider then a JCC matrix, which is 0, 1 matrix, such that entry 1 is if there exists edge between vertices Vi and Vj, and 0 otherwise. Then we consider diagonal matrix of vertex degrees, and then a Laplacian matrix is the difference of D of G and A of G. So it is well known that then this matrix is symmetric, semi-definite, and then we can order its eigenvalues in non-increasing order, and moreover, the least one is equal to 0. Okay. Then what is a chain graph? So there are several equivalent definitions for a chain graph. One of the simplest one is to say that this is 2K2 C3 C5 free graph. C3 C5 free means that is a bipartite, and then we have another requirement that is that 2K2 configurations are also forbidden. So as I mentioned, they are important because in the class of all connected graphs of fixed order and size, which are bipartite, then those with maximal largest eigenvalue or Laplacian or sinus Laplacian are chain graphs. Another way to see them, which will be important later here, is to define them structurally. So this is a bipartite graph, so we have two independent sets, two color classes, and then the edges are, there exist only these cross edges, which are associated, as you can see here. So we have here the same number of cells in the one color class and the same number of cells in the other color class, and then here with the connect all vertices in U1 with all vertices here on the other side, then those in U2 we start from V1 up to VH1 and so on. So we see that there is a certain nesting property. So the set of neighbors of UH is connected to the set of neighbors of, is a subset of the set of neighbors of UH minus 1 and so on. And then that's the reason why these graphs are also known as double nested graphs, because we have double nesting property from left to the right and also right to the left. So if we know cardinalities of all these cells, then the shorter way to denote this chain graph is this one, okay? So where we point out here cardinalities of the cells in each color class. Then what would be important for us are also Ferrer diagrams. So if we consider partition of the 2m, m is the number of edges, then this partition can be represented using a Ferrer diagram, which is left justified array consisting of L of pi, which is in this case n rows of boxes, and the ith row contains pi boxes. Then we also define what is a conjugate of the integer partition pi, we denoted by p star, and this is basically when we consider the transpose of the Ferrer diagram. So in that case, we are counting in pi star, we are counting the number of the boxes in the ith column of f of pi. So, for example, if this is a Ferrer diagram which describes partition of number this integer partition of number 16, then the conjugate is this integer sequence. So you are counting now the number of the columns in this Ferrer diagram. Now, what we first consider is when we work with bipartite graphs, we consider degree sequences in two color classes. So we have two degree sequences, pi for one color class and the other one for the second color class. And we want to see when there exists a graph, bipartite graph with these integer sequences as degree sequences. So as you can expect, this is not, if you take any two integer partitions, then you cannot always find a bipartite graph with the degree sequences. So there are some results which say when there exists a bipartite graph with these degree sequences. So, and for this characterization, it's important how do we introduce an order between two degree sequences, not degree sequences, sorry, between the two integer partitions. So we say that alpha majorizes beta if these two conditions are satisfied. Okay, so then. There exist these two theorems, which I mentioned, that they can help us to see when two integer sequences are bipartite graphic, means that they are degree sequences of bipartite graph. So if and only if the conjugate of tau majorizes pi. Okay, this is one condition, and in case we let that tau conjugate of tau is equal to pi, then this guarantees that this is a chain graph sequence, means that there exists a chain graph which has these integer sequences as degree sequences. Okay, what is our contribution? That we proved that if we have a pair pi and tau of chain graph sequences, then up to isomorphism there exists chain graph sequences means the tau conjugate is equal to pi. Then up to isomorphism there exists exactly one chain graph whose color classes have degrees pi and tau. And moreover, not exactly one chain graph, there exists exactly one bipartite graph whose color classes have degrees pi and tau. So since the degree sequences of chain graphs are conjugates of corresponding Ferrer diagrams, so in the example that I presented, so if this is integer partition of number 16, then you can deduce that what is a unique chain graph which has degree sequences pi and pi conjugate, and this is the graph in question. So as I mentioned, we wanted to see what is the relation between graph sequences, chain graph sequences, and the Laplacian spectrum. So we wanted also to calculate what is the spectrum of chain graph. And then chain graphs admit equitable partitions, so we can use these cells to form an equitable partition of a Laplacian matrix. And then using well-known things from spectral graph theory, we know that this what we call a quotient matrix D of G, the characteristic polynomial will be factor of characteristic polynomial of Laplacian matrix, and we will also have degrees of vertices in these cells U1 up to VH. This is a consequence of the fact that that vertices in each of these cells, they have a common neighborhood, and this implies that then their vertex degrees will appear in spectrum with multiplicity cardinality of the set -1. Okay, where this di and di star, they stand for vertex degrees in U's and V's. Okay. So we see that vertex degrees will appear in the spectrum if these numbers are greater than or equal than 2, and the rest will be eigenvalues of this quotient matrix. Okay. So when we want to calculate then what is the characteristic of this quotient matrix, it will appear surprisingly one three-diagonal matrix, which is obtained after some elementary row operations applied on the quotient matrix. And then this determinant can be calculated explicitly, and we get explicit form for the characteristic polynomial of the chain graph. Okay. So then what we can say about the spectrum of chain graphs from this expression. First of all, we can say that it is well known that the eigenvalues of three-diagonal matrix are all simple. So based on this relation we established with the diagonal matrix, we can conclude that the eigenvalues of the quotient matrix are all simple. Then we can provide one algebraic way to see if given degree sequence is a degree sequence of a chain graph. Okay, so because in that case, then determinant of the previous matrix that I considered here, this triagonal has to be 0. Okay, and then if we can get a condition which guarantees if a given pair of monotone positive integral sequences is not a chain graph sequence. Okay, so if here this k is not equal to L, or this determinant is not equal to 0, then we know that this sequence cannot be, this pair of sequences cannot be a chain graph sequence. Another thing that we considered is when you have a spectrum of chain graphs, you know that some eigenvalues will be degree sequences, and some of them will be eigenvalues of the quotient matrix. So we asked ourselves when maybe some vertex degree will be also eigenvalue of the quotient matrix. And we provide necessary and sufficient condition. Okay, which says that a vertex degree D will be also an eigenvalue of the quotient matrix if and only if this we find that vertex degree appears on in both color classes, so it's equal to di and also di star. So it's equal to some vertex degree in the color class U and also some vertex degree in the color class J, provided that the sum of these indices has to be different from h plus 1 and h plus 2. So an example here shows we have this chain graph, then we deduce what are its degree sequences. And for example, here number 9, degree 9 appears 2 times, which means that from this part we will have 9 with the multiplicity 1. Here 9 is multiplicity 3, so this guarantees that 9 will be eigenvalue with multiplicity 2. So this gives in total 3. But on the other side, when you calculate degree D1 and D1 star, you will get 9. These two numbers are equal. When you add 1 and 1, you get 2, which is not equal to 4 of I, because here the height is free, and then you will get that 9 will be eigenvalue with multiplicity 4. So this all can be applied in control theory. So we consider the set. We take some graph G, and we consider this block partition of Laplacian matrix of graph G according to if the vertices of the graph belong to some set that we call leaders or followers. Okay, and then the control system we consider is a leader-follower system, which is given by this equation, and then the followers evolve through the Laplacian-based dynamics, which is given with this equation. And U denotes the external control signal ran by the leader states. Okay, so this is the definition, but then it has its algebraic interpretation, which is given first here. We say that this system described by 1 is said to be controllable if it can be driven from any initial state to any desired state, final state in a finite time. And in this study, we want to determine locations of the leader under which the controllability can be realized. And then, as I said, there is one algebraic conditions which tell us when we can do this. So this Kalman's controllability rank conditions says that this system is controllable if and only if this matrix has a full rank. Okay, and another useful conditions that we used is this one. So it says that the system is controllable if and only if the following two equations are not met simultaneously. So we cannot find eigenvector of this submatrix which is orthogonal to the columns of this submatrix. Okay. So in this study, it appears that some you see also, yes, that some matrix, this submatrix has to have a distinct eigenvalues. Okay, so it makes sense to characterize some matrices which have distinct eigenvalues, and this motivates us to consider chain graphs, because with what I presented previously, we can conclude, we can determine chain graphs which have distinct eigenvalues. Okay, so based on the theorems I provided before, we can conclude that the chain graph will have distinct eigenvalues only in case if these parameters that define chain graphs are either 1 or 2. Okay, and then we have here necessary and sufficient condition when a chain graph will have distinct eigenvalues. In particular, if we focus, for example, so we know that all of these entries will be either 1 or 2. So if we focus on the case where there is exactly 1, 2, only 1, 2, we have here the description of chain graphs which will have simple eigenvalues, and then we see that using these algebraic conditions for controllability, that this system will be single leader controllable. So we just need one leader to have this system to be controllable, and then that this controller has to be, the leader has to be or one of the vertices which is co-neighbor, means where in this cell there are two vertices. Okay, so as you can see here, then in example, if you consider the chain graph of the height 2, then if you place here 2, then this graph will have all simple eigenvalues, and this vertex which belongs to this U3, I put it here separately, will be a leader and will make this system controllable. Okay. So this work was supported by research sector of Kuwait University with this grant, and these are some of the main references we used. Okay. But there are more. Thank you.
Thank you, Milisha, for the interesting talk. Yeah, audience, if you have any question, we can ask now.
Sorry, I don't know where.
Okay, so I have.
I lost. Okay, yes.
Can you hear us?
Yes, I can.
Yeah. So one quick question about co-spectrality. These chain graphs, are they determined by their spectrum, by either adjacency or Laplacian?
Yeah, no, for the adjacency spectrum, this is an open question because it is, as in this case, when you calculate the spectrum, you get that one part of the spectrum is calculated using a 3-diagonal matrix. And there is one paper which I mentioned here, I think in the references, this is reference number 2, where we left this as an open problem. Okay, and it seems, when you read it, it seems very easy to understand. And it seems also easy to prove, but it's not. Okay, so it is related to some, I would say, spectral properties of 3-diagonal matrices. And so far, we were not able to answer this question for the adjacency spectrum. For the other spectrums, you know, Laplacian and sinus Laplacian for the bipartite graphs are equal. I mean, the spectrum is equal. So, but about this spectral determination, I don't know anything yet. I was not thinking about it.
Are there other questions? Okay, if not, thank you, Melissa, for your interesting talk. Thank you so much.
Welcome.
Okay. Our last speaker is Krishna Kumar from University of Kerala, Thiruvananthapuram. Krishna?
Yeah, yes, Dr. Rajesh.
Yes. Yeah. Have you sent the videos?
No, I am presenting. Can I get the control?
Okay. Okay.
Militia, please stop sharing your screen. Sir, you can try now.
You didn't get control. Your request for control was not accepted.
Sir, can you try now? Because Miss Militia has stopped sharing her screen.
Can you see my screen now?
Not yet.
Just a minute. Is it?
Yeah. Oh, we can.
Now, is it? It's full screen.
Yes, full screen.
Yeah, okay. Thank you, Rajesh. And I thank the organizers for giving me an opportunity to present my work. My title of the talk is Condition Eigenvectors of Bounded Linear Operators. So these are some notations that we are using. We are considering a complex separable Hilbert space, capital H, and BLH denotes the algebra of all bounded linear operators on H. To present some basic definitions about collection of all eigenvalues of a bounded linear operator is set of all lambda such that Ax equal to lambda x for some x not equal to 0. And also we have something called approximate eigenvalues of A denoted by sigma suffix A of A. which is collection of lambda such that axn minus lambda xn goes to 0 for some sequence xn which is not equal to 0. And we have something called the spectrum of A, which is collection of all lambda such that A minus lambda is not inverted. So these notations that we are using. And I will straight go into one of the equivalent definitions of what we known as epsilon condition spectrum of an operator in BLH. It's denoted by sigma epsilon of A, and the parameter epsilon lies between 0 and 1, which is equal to sigma of A union set of all z in C such that norm of zi minus A of x less than or equal to epsilon into norm zi minus A into norm x. Please note that whenever epsilon equal to 0, sigma epsilon of A becomes sigma of A. So it's kind of a generalized set or a set containing sigma of A. When we come to the definition of what the term epsilon condition eigenvector, you just look into the definition of condition spectrum, and suppose we have norm zi minus A of x less than or equal to epsilon into norm zi minus A into norm x, then Z becomes the condition eigenvalue and the X becomes the condition eigenvector, and obviously it depends on the parameter epsilon and Z. So exactly X becomes the epsilon condition eigenvector of A corresponding to the epsilon condition eigenvalue Z. So keeping in mind these definition of condition spectrum and condition eigenvector, so why condition spectrum? So why condition spectrum is for many reasons, and these are some reasons why the importance of condition spectrum. Spectrum are sensitive to perturbation, but condition spectrum is not. And spectrum or eigenvalues fail to identify the norm behavior of the matrix or operator, but condition spectrum becomes useful for identifying the norm behavior of a matrix or operator. And spectrum are generalized in many ways for various reasons. Among that one, condition spectrum is found to be algebraically close to the spectrum. For example, we can see that both spectrum and condition spectrum are Ransford spectrum. Ransford spectrum is some kind of identification of spectrum in some direction. Then what we have done in this particular work is we have considered the following two classical results that we have. Suppose we have two matrices which are commutative, then we know that they have a common eigenvector, and also an eigenvector guarantee an operator an invariant subspace, and or a common eigenvector guarantees a common invariant subspace for a couple of operators. For example, if A and B have common eigenvector, then we may say that A and B have a common invariant subspace. So what are all the problems that we have considered is whether we have suppose A and B are almost commutative, then whether A and B share a common epsilon condition eigenvector for sufficiently small epsilon greater than 0. Do the approximate eigenvalue guarantee an almost invariant subset? So instead of invariant subspace, we are looking into kind of generalization of invariant subspace, which is known as almost invariant subset. So the connection between approximate eigenvalues and condition eigenvectors we have considered, and also that we are looking into. Also, we are looking into the common condition eigenvectors. Do they guarantee a common invariant subset? So these are some problems that we have considering, and also for these problems we need some definitions, and these are the definition of almost commutative. So depending on a parameter epsilon, when we say that two operators are almost commutative. For example, if norm AB minus BA less than or equal to epsilon, then we say that A and B are epsilon commutative. If epsilon is sufficiently close to 0, then we may say that it is almost commutative. And we are also giving the definition of kind of generalization of invariant subspace. That is, we are saying something about an invariant subset or almost invariant subset. that is also depend on a parameter epsilon. And suppose we have a subset G of H and A belongs to BLH, and we need to say that when we can say that G is an almost invariant subset under A if it satisfies for every X in G there exists a Y in G such that norm AX minus Y less than or equal to epsilon, then G is called an epsilon invariant subset of H under A. Okay. If epsilon is sufficiently close to 0, then we say that it is almost invariant subset. And note that in both these definitions, whenever epsilon equal to 0, it becomes A and B. First one becomes A and B are commutative, and second one becomes like G becomes invariant subset under A. And these are these are some results in connection with the in the direction of epsilon condition eigenvectors. And from the definition it follows that whenever a vector is epsilon condition eigenvector for some epsilon greater than 0, then it is then it becomes delta condition eigenvector for every delta greater than or equal to epsilon. And it also says that a const or scalar multiple of an eigenvector is, or condition eigenvector is also a condition eigenvector. That's the second one. The second result shows, and the third result shows that whenever X belongs to an epsilon condition eigenvector of A, then X belongs to lambda A's condition eigenvector with respect to the condition eigenvalue lambda z, and here epsilon becomes something like mod lambda into epsilon. And like eigenvectors, the sum of two eigenvectors may not be an eigenvector. Like this is not true for condition eigenvectors. Then this we have given an example to show that sum of two condition eigenvectors may not be a condition eigenvector. And for that one we have considered this example. If you consider A like this and X and Y like this, where X in X and Y the 1 and minus 1 appears in the nth position, then we can show that these here we have considered the norm to be infinity norm. And we can show that this happens, and it turn out to be that both X and Y becomes the epsilon by n minus 1 into n plus 1 eigenvector of A, but X plus Y may not becomes the epsilon by n minus 1 into n plus 1 eigenvector of A. And this lemma we required for the remaining results. Keep it in if A belongs to BLH and rho of A, which is supremum of A minus lambda I, where lambda belongs to sigma of A, then we can show that for every Z in C, rho of A becomes less than or equal to 2 times norm A minus ZI. And this is a proof, and this is an easy proof that you can see. And what happened is in the beginning I mentioned that we are looking into the connection between approximate eigenvalues of A and condition eigenvectors, and this is the result that we can connect between the approximate eigenvalues and the condition eigenvectors. We can show that let A belongs to BLH, and if lambda is an approximate eigenvalue of A, if and only if lambda becomes an epsilon condition eigenvector of A for every epsilon greater between 0 and 1. And this is another result. We can show that the connection between approximate eigenvalues and epsilon invariant subset. It's turned out that if lambda belongs to sigma of A, sigma A of A, and mod lambda less than or equal to 1, then we can say that H has an epsilon invariant, or we can prove that H has an epsilon invariant subset and array for every epsilon greater than 0. And this is another result that we got. If A belongs to BLH and H has a one-dimensional epsilon invariant subspace under A for some epsilon greater than 0, then we can find a lambda epsilon belongs to the new sigma f epsilon of A lambda epsilon not equal to empty, which means that we can find an epsilon some f epsilon condition eigenvalue for A whenever A has an epsilon invariant subspace. And this is the famous singular value decomposition for like finite rank operators, and we have found a simple, very simple proof using basic algebraic techniques. And this is one version of the singular value decomposition theorem, because for the remaining proof we have widely used the singular value decomposition of finite rank operators. So first what we have proved is, this is one of our main result what we have proved is, if A and B are almost commutative, then we can find a common eigenvector for both A and B. Or we can show that nu sigma epsilon of a lambda intersect with nu sigma epsilon b of mu. This is something generalization of if A and B are commutative, A and B have a common eigenvector that we have generalized to condition eigenvectors. So we have shown that whenever two matrices are almost commutative, we can find a common eigenvector corresponding to both operators. Then we have extended this whatever we have proved for matrices to operators with one of the operators is finite rank and the other may be any bounded linear operator. And the theorem becomes little like the epsilon becomes something like g epsilon, but g epsilon we can explicitly calculate and show that g epsilon goes to 0 whenever epsilon goes to 0. So both this becomes like the classical results whenever epsilon equal to 0. And then we have from finite rank operators we have considered the compact operators. We have shown that the same result is true for the whenever one of the operators is compact operator. And more generally, if one of the operators is a something like alpha I plus k, which is one k is compact, then the same results may be proved for whenever the two operators are almost commutative. And this is an example like this in the finite dimensional case. If you have A and B, then we have sigma of A is equal to this one 1 minus 1 0, and sigma of B is equal to 1 1 by 2. Then we can have AB minus BA becomes this one, and norm AB minus BA under the infinity norm becomes 2 epsilon, and for that one we can show that there exists a common eigenvector for both A and B. And these are some references, and thank you. Hello?
Yeah. Thank you, Krishna. Thanks a lot for interesting talk. Yeah. Other questions for Krishna? If not, let's thank Dr. Krishna Kumar for his interesting talk. Thank you, Krishna.
Yeah, thank you, Dr. Rajesh.
Thank you. Thank you all the participants for the wonderful presentation. I also thank Professor Rajesh Kannan for chairing this session. Thank you very much, sir.
Yeah, thank you.
Thank you, sir. I request all of you to join Professor C.R. Rao Hall. The next session will start at 1:30 after a lunch break. Thank you. Thank you so much. Thank you very much, sir.
Yeah, thank you.
Thank you, sir. I request all of you to join Professor C.R. Rao Hall. The next session will start at 1:30 after lunch.